welcome to the lesson on acids and bases. So today we're going to, because of the delay stuff, some people have to watch this video and I apologize. Okay, so in bio you learned that, even in regular bio probably, that acids are substances that release H+, and a base is something that releases OH-. In AP Chem, they're going to use a different definition, which is known as the Bronsted-Lowry definition. And there, acids will act as proton donors, or they release protons into the environment, which is the same as saying releasing H+. But instead, bases have a separate definition as opposed to releasing OH. Bases are things that accept H+, or gain H+. So, because of what is a proton? And a proton is produced when you put an acid in water. This is a strong acid. Hydrochloric acid is a strong acid, so it completely dissociates into H+ and Cl-. Okay, and what happens is that chlorine is very, very electronegative. Okay, and H atom has one electron. Okay, so when you put this in water, what happens is chlorine takes that one electron. Okay, and then you're left with the hydrogen ion without an electron is just a proton. Okay, so essentially H+ is just a proton. Now, okay, what happens, okay, when H+ is in water, okay, is that the H+, okay, so this H+ from hydrochloric acid, okay, actually hops onto water, and water becomes what is known as a hydronium ion, or H3O+. Okay, and then we have the Cl- that's released. Okay, now these two reactions are equivalent. This one is written with water, okay, and this one is written without water. Okay, but they're equivalent. Here we're just not showing that what happens with the H+ is the H+ hops onto the water and produces H3O+. Okay, these two are interchangeable. They mean the same thing. So you could say when you put an acid in water, it produces H+, or you could say when you put an acid in water, it produces H3O+. Those are the same thing. Okay, now we're going to look at an example of a Bronsted-Lowry acid reaction. Always on the AP exam, they ask you to like identify what is acting as a Bronsted-Lowry acid. So if we take a look at HF, if we look at what it becomes in the other reaction, let me get the pen out. So if we look at what it becomes, HF becomes F. It has lost a proton, so therefore it is acting like an acid. If we take a look here what happened to water, water gained an H, or gained a proton. Okay, and so therefore it is like acting as a base in this example, so it's gaining protons. Now, this is a weak acid, so notice that we have an arrow that goes in both directions. Okay, so that means this is equilibrium. So this reaction can also go in the reverse direction. But if we look at the reverse direction, in this reaction, HF in the reverse direction, and let me get a different color, we'll use red, okay? In the reverse direction, F accepts an electron, it becomes HF. So here, in the reverse direction, F is acting as a base. And this hydronium here loses an H and becomes water, so it's acting like an acid. Okay. And these are pairs, okay, which we're going to learn to identify more directly in the next slide. So here we have the same sort of reaction, but now instead of having an acid with water, we're reacting with a base with water. So we see what happens to NH3. NH3 accepts a proton and becomes NH4. So here, because NH3 is accepting a proton, it's acting like a base. Now, water in this case loses a proton, or loses an H+, and becomes OH-. Okay. So now these are known as pairs. A base, when it is reacting, produces a conjugate acid. Okay. And an acid, when it's reacting, produces a conjugate base. So the goal of the first part of this lesson is to be able to identify the acid, the base, and then the acid's conjugate base, and the base's conjugate acid. And on the next page, we're going to practice that. Okay. Oh, before we actually practice that, there's the next slide. So something can be, which I can never pronounce this word correctly, amphimorphism, which means it acts as just an acid. It can act both as an acid and a base. And water is doing this. Here in this reaction, water is losing an H+, and it's acting like an acid. Okay? And in this reaction, water is gaining an H+. Okay? And it's acting like a base. Okay? So there are substances that can act both like an acid or a base depending upon what they're reacting with. And that's this word, which I can't say, is the word for that. Okay? Now, things that can act this way tend to have multiple H's. Okay, that they can either gain an H or lose an H, but they tend to have multiple H's, so they can do both, gain and lose. Okay, so now back to the identifying the conjugate acid and base pairs. So every acid in a reaction has a conjugate base, it's what it becomes, and every base in a reaction has a conjugate acid in the products. And our job is to recognize those pairs. So if we look at this, this becomes that. Okay? And if we look at what had happened, this is acting like an acid because it lost an H. So this is the acid, which we're going to write as A. And this is its conjugate base. It's what it becomes. Okay, so CB, conjugate base. Okay, so why that is, okay, this is an acid, it loses an H+, and it becomes its conjugate base. But this, when reacting in the opposite direction, okay, this is accepting an H+, so it's acting like a base. If you look at what's happening here, this is gaining an H+, okay, so this is acting like a base, okay, and this is its conjugate acid. Okay, what I would do now if I were watching this video is I would pause it and see if I can do B and C, and then come back and look, but if you don't want to, you don't have to, obviously, I hope no. So this, if you take a look at what happened, this gained an H, it became this guy. And really, we should be saying H+. So this is, it gained an H, so this is a base, okay, and this is its conjugate acid. Now, what this guy did, okay, this lost an H. If you take a look, this is missing an H. Okay, so this is acting like an acid. Okay, so this is the acid, and this is its conjugate base here, Cb. Okay, one more example, and this should actually be a plus here, so that's a typo, +2. So look, this was C2H5, and it gained an H, it became C2H6. Okay, so this is the base. Okay, and this is its conjugate acid. Okay, and then here, this lost an H when it became that, so let's choose another color. So this is acting like an acid. Okay, this is an acid, and then this is its conjugate base. Okay, now we're going to summarize acid conjugates and base conjugates. Okay, so an acid's conjugate base, basically what the acid becomes, okay, will always have one less H, and the total charge will decrease by -1 because it's losing something that's positive. And a base's conjugate acid will always have one more H, because remember bases gain H, and the total charge will increase by +1. So the first question is, what would be the conjugate base of this? So basically, this is an acid. What does it become when it acts like an acid? So it's going to lose an H, so it's going to be H, right? Only one, PO4, which I'm writing with not the pen, PO4, I'm writing with the mouse, okay? And it says that its total charge will decrease by 1. So it's already -1, so it's going to become -2. So that should say, even though it barely does, HPO4 -2. Okay. Now, what would be the conjugate acid of H2PO4? So that means that this is acting like a base, and we want to know what it's going to become when it acts like a base. So it's going to gain a proton, because it's acting like a base. So it's H3PO4. Okay, and we said now it gained a hydrogen. Hydrogens are positive, so it's going to become more positive. Okay, and its charge is already -1. Its charge is already -1. And it's going to become more positive, so now its charge, since it gained 1 H, it's going to be neutral. It's going to become more positive, so it's -1, and then it's neutral. Okay. So we have one more part of this, which we're going to talk about Ka. Okay. So strong acids, as we discussed, completely dissociate into ions. Okay. So there's none of when you put a strong acid into water. Okay, it completely dissociates. There's none of this left, and that's why we have the forward arrow. From equilibrium, we learned when things go in the direction of the products, K is huge, or much, much greater than 1. Okay, weak acids dissociate very slightly. Okay, so most of it will still be left in the acid form. Okay, so weak acids have Ks that are very, very, very small, or less than 1, because they favor the reactants. Okay. Now, if we were going to write a K expression for either of these reactions, let's say we're writing it for this one, okay? Remember, K is products over reactants, we don't include liquids. So here, the products would be A, so this went in here, this went in here, and then this was the reactant, so it's on the bottom. Okay. Now this is a special K, called Ka, because it's the Ka for an acid. Okay, but it's no different than the K that we learned when we did equilibrium. It's just now we're talking about it for an acid, so they call it the Ka. This is just saying that when you have a strong acid, it completely dissociates into its conjugate base, which is this is the conjugate base, and H+, or hydronium. And there's none of the acid that's not ionized left. And this is the strong acid list that we learned in October. You still need to remember these strong acids. Right? We tried to memorize these in October, and these you still need to have memorized. Weak acids, on the other hand, okay, not much of it ionizes. So you still have a lot of the unionized acid left, and only a little bit of H+, and a little bit of its conjugate base. Most of it is still left in the unionized form. Okay, so for Ka, okay, the higher the Ka, the stronger the acid. Okay, and the reason why that is, okay, is that, remember, if you have a high or a large Ka, the higher the Ka, or the higher the K, it favors the products. Okay, so that means if you have an acid-base reaction, okay, where we have our acid here, so we have our acid here, if the Ka is bigger, it's going to favor the products more, and it's going to favor more dissociation. Okay, so the bigger the K, the stronger the acid, or the greater dissociation you're going to have. Now, Kas are usually in scientific notation, so they're considered to be like, if you be something like this, 1.8 times 10 to the negative 8, so they're annoying numbers. Okay, so scientists or chemists have made something called the pKa, okay, which makes it a nicer number, and pKa is equal to the log, just log base 10 of the Ka. Okay, now this is a practice of sort of everything that this goes through, and I actually pre-wrote out the answers, so you can just follow along, or you can get a piece of scrap paper and write the answers and see if you're right. So it says, write the reaction of acetic acid with water. So here we have water, and here we have acetic acid. Acetic acid is acting like an acid, so it's going to lose its H+, and we're going to become a hydronium ion. And this is this without the H+, and it now has a minus charge because it lost a positive proton. Okay, this is the reaction with nitrous acid, same thing, H2O and water. This loses its proton, and this becomes H3O+, and since this lost its proton, it becomes NO3, and now it has a -1 charge. For the Kas, products over reactants, so for the Ka for this reaction, the Ka expression, this goes on the top, so does this, and on the bottom goes the acid. We don't include water because it's a liquid. And again, okay, the Ka is always H+, the conjugate base, and then the acid. And then same thing here you can see for the nitrous acid. Okay, now, it says the Ka for acetic acid is 1.8 to the -5, and the Ka for nitrous acid is 7.1 times 10 to the -4, which is the stronger acid. So nitrous acid is a stronger acid because it has a higher Ka. Okay, so what that means is that the reaction favors the products more than the other one, and that means there'll be more dissociation of H+, or more ionization. So higher Ka, okay, the products of that one are favored more than the other, and that means more H+ is produced. Question 5 asks you to calculate the pKa. Okay, and you need a calculator for this. So pKa is equal to the negative log of the Ka. Okay, so what you do is you get your calculator out, you press log, the regular log, not ln, and then you enter the Ka. Okay, and you're going to get a number. So log 1.8 times 10 to the -5, you get a number. Okay, and then it's going to be negative, so then it's a negative log of the Ka, so you're going to make it positive. So if you did that on your calculator, you got 4.7. Okay, and then you're going to do the same thing for this one. Press log, enter the Ka, okay, and then make the number positive. And that's the Ka. Now you'll see, which you can barely see because of the, this smart or limited mode, okay, that this is nitrous acid, this one, okay, it has a smaller pKa, okay, and that was the stronger acid. So the relationship between pKa and acid strength is the lower the pKa, the stronger the acid. Okay, and that is actually the reverse of the Ka. The Ka, the higher the Kpa, the stronger the acid. So you got to sort of remember those things. One way to remember this is if you remember pH. The lower the pH, the lower the acid. So that's like the same thing with the pKa. All right, that is the end. Tomorrow in class, if there's a delay, we'll have a do now to see if we learned. Okay.